we were looking at the sort of the most basic or most common recurrence relation that comes up, where you're dividing into two different pieces, subproblems. That's the two, and then the division is half each. These two could vary in other kinds of problems. And then you're combining the answers in something which is in time proportional to n, the number of these. So we've seen merge sort, and last time we saw the problem of computing the minimum number of, computing not the minimum, but computing the number of inversions in a given permutation. And then you have the problem of a related problem where the permutations are generated on a tree. All right. And all you have available to you is the flipping at each node, each internal node of the tree, to generate those permutations. Okay, so today I'm going to show you another, start off by showing you another divide and conquer algorithm that has the same recurrence relation, so the analysis will be, time analysis will be very similar. The issue is always here. This tends to be the problem. How do you actually do the combining or the merging of the two subproblems in time that's actually proportional to n? That's usually the trick. And this is a particular problem that has had some real application, closest point problem. And so here, the problem is that you have points on the plane. Okay, so it's on, like on the blackboard. So n points. And between any pair of them, there's some distance. So whatever distance, straight line distance between these two, this straight line distance is shorter, obviously. You can just see that by looking at it. This looks even shorter, and just by looking at it, that looks like, unless this is a contender, one of these two looks like the shortest distance among all pairs of points that are on the plane there. So we want to find the pair, or if in case there's a tie, I could say a pair with the smallest distance between them. Euclidean distance, straight line distance. Okay, well, obviously you could just compute this directly for every pair. There are n choose 2 pairs, roughly n squared, proportional to n squared, and you could just grab a pair at a time. Each point is specified by an x and a y coordinate, so nothing too surprising there, how we're representing the points. And you could certainly just, if I grabbed a point here and a point there, then I use Pythagorean, whatever. You can, we all know how to compute the Euclidean distance between a pair of points in terms of their x and y coordinates, okay? So you could do that. So certainly order, I would say theta n squared operations suffice. Okay. For each pair of points, the amount of arithmetic that you're doing to figure out what their distance is some finite number independent of n. Just depends on knowing their two coordinates and doing a little arithmetic, squaring, taking a square root, whatever. But so that's some fixed number of operations per pair. But if you did it that way, you would have something on proportional to n squared pairs to look at. And our goal is obviously going to be to do this faster. I should mention something that the book mentions. Divide and conquer often, not always, but often is a method that speeds up algorithms, or speeds up, gives you a faster solution to problems that already have reasonably fast solutions. So a solution that runs in n squared time is reasonably fast. It's polynomial time. That's the distinction that's made. This is a polynomial in n being the size of the input. And the divide and conquer is going to improve this from n squared down to n times log n. Okay? Now, it's not always true. There are some examples where divide and conquer is a technique that's used that gets us from something which is exponential time down to something that's polynomial. So the comment they were making isn't always true, but it's often true. Still, a very valuable improvement to go from n squared down to n times log n. And the book has some gee whiz numbers at the beginning, and most books like this do, where they show you how fast n squared grows as compared to n times log n. And there are definitely applications where having an algorithm whose running time is proportional to n log n made the problem practical to solve, whereas in n squared it was not practical. Of course, it all depends on the size of n that come up in the real applications. I'm just emphasizing this because, in fact, I didn't have a good intuition about the difference between n squared and n log n. Gut feeling appreciation for that until I actually wrote some programs and ran them intentionally. One running in n squared time, the other one the algorithm with n log n time, and you don't have to push up in those applications. I didn't have to push up n very large before I really started to see the difference. One, I was sitting there waiting for the output or the program to finish, and it was really annoying. And the other one came back in the blink of an eye. And that was, as n got bigger, I ended up waiting more, an hour, 2 hours, and the other one was just finishing instantaneously. So moving from n squared down to n log n can really be important depending on how big n is. All right, so we're going to find this in n log n time. Make another comment about these things. Another reason why we go from n squared down to n log n is because we can. And because we can, it informs us about the nature of computation. So I once went to a lecture given by a statistician that was essentially about this kind of a problem. They needed to find the closest pair of points. These points represented something, had some meaning, and they were big. These are like all the stars in the sky. That's 100 billion or so that we can see, and that makes n very large. And he was saying it's really unfortunate that to solve this problem, you have to look at all pairs of points. It was just absolutely obvious to him that you had to. This is just what nature required. It never even occurred to him that might not be true. And so, again, I think it's useful, therefore, to have this kind of thing that you can pull out and say, well, your intuition about computation isn't that well developed. It doesn't necessarily require n squared operations. You don't always have to look at every one. Okay, so having said all that, how do we solve this problem? Well, I said it was divide and conquer, so what's an obvious kind of division? Yeah, left or right, or up or down, or some diagonal. That would be a little more clumsy. But yeah, left or right, left and right will do. So how are we going to do that efficiently? How do we divide efficiently by left and right? Obviously, we want about half to be on the left and about half to be on the right. And how do we figure that one out quickly? How do we grab about half of them to be on the left and half of them to be on the right?
Take the leftmost and rightmost points, just divide that by 2.
If we take the leftmost point and the rightmost point and divide that by 2, that won't necessarily capture half on the left and half on the right, because their spacing is uneven. Yeah.
Median?
Well, okay, that's the right word, is the median, but how do we find the median of?
We do a median of medians.
You what?
We do a median of medians.
Do a median of medians? Too complicated. Yeah?
Can we use the line x equals to y and then divide the plane into 2 parts?
You want to take that line? But again, we wouldn't necessarily have half on this side and half on that side. We don't know. Yeah. Yeah, a voice from the wilderness. Yeah.
Okay. What about taking the x-coordinates and sorting real quick and taking halfway?
Right. We could take the x-coordinates of all the points and sort them. I heard the expression real quick. What does that mean? Okay, we know we can sort in n log n time. We saw merge sort, and everybody should know that anyway before from a previous course. So we can sort n points in n log n time, and we can take advantage of that. So, or n numbers in n log n time. So we can go through the points that represented each point by an x and y coordinate. And so as a first step, we could sort the points by their x coordinates. Okay, so let's call that into a list called x. Okay, so they're sorted now by their x coordinate. And we can certainly do that in order n log n time. N log n time. And then certainly we can just find the middle entry. Now we're not talking about the middle in terms of its position, but the median entry in the sense that half are to the left and half are to the right. That's certainly doable. It's going to turn out it's also useful. It's going to be also useful to have a list of the points sorted by their y coordinate. It may not be obvious. Well, it shouldn't be obvious yet why we want that, but we can certainly do that at this point. So we're sorting the original set, not this one. We'll sort the original points. Well, I could have said this one too, because we're going to resort by their y coordinate, by their y coordinates into a list. Let's call it y. And again, you can do that in order n log n time. And 2 n log n's are still order n log n. So so far, we're within the time bound that we've advertised and we're shooting for. Okay, so this is going to be reduced to n log n. Okay, having done that, well, we just said what we want to do is divide the points into a left side and a right side, roughly half on the left and half on the right. So divide the points into a sublist P and Q sublists with half with all points in P to the left of all points in Q, two equal-sized, roughly equal-sized. Okay, so just looking at this, this is going to be P, this is going to be Q. Got about half over there, and well, this is drawn so it looks like it's also the middle of the x range. That wasn't intended. It's the middle, it's the median point of the points sorted by their x coordinates. Okay. And then divide and conquer. What's a name for this problem? Closest point. Okay, called the closest point problem. I'm following the logic that's in the book. If you read the section on this algorithm, you'll see it's the same, but I'm not using their notation. So I'm just calling this the closest point. So we want to find closest point among all n of those. Let's see. What's the original set called? I don't know. Capital N of size n. All right. N points. Set n of points. And so over here, once we've divided them, divide and conquer means we're going to find the closest point problem in P which has n over 2 points. And we're going to solve the closest point problem in Q, which has n over 2 points. So solve subproblems like that. And then we're going to somehow use the solutions that we got here plus some additional work so that in order n time, we're going to find the closest pair of points over all of these points in the set n. So use the two sub-solutions and something on the order of n new operations to find or to solve closest point problem in n. Okay. So as in all these divide and conquer kinds of things, this is where all the real work is being done, where the interesting aspects, interesting details of the algorithm are going to be done. And just as in the counting of the crossing lines we looked at, we know what the closest pair is among points where both points are in P. That was solved as a subproblem. We know what the closest pair is among pairs of points that are in Q. So what's left to consider is just pairs where one point is in P and one point is in Q. Okay? Well, how many pairs of points are there? How many pairs in P and how many pairs of points where one is in P and one is in Q?
N squared over 4.
N squared over 4. So that doesn't really help because we're trying to do something which is proportional to n. And so, yes, we have fewer points pairs than before because before we had something like n squared over 2, but now we have something that looks like n squared over 4, but that still isn't going to be helpful enough. Any other ideas?
Well, you have two sets of closest pairs, so you can use that to limit the points you have to consider.
Okay, yeah. And did you have another comment?
Yeah, same thing. Can you just look at the points close to the border?
Yeah, sort of intuitively, you don't want to look too far to the left and too far to the right. I mean, somewhere along the border here is probably where the candidate pairs are going to lie. Of course, it may be that all the n over 2 points in the left side really are very close to the border, and so they are in terms of the right side. So you can't necessarily, that comment alone will not limit the number of pairs below n squared. And we could still have, in worst case, some kind of n squared behavior. So we're going to have to look a little more closely at the geometry and make some comments, make some observations. All right, well, let's say that the closest pair of points in P had a distance delta P. And the closest pair of points in Q we found had a distance delta Q. Okay, those were the two closest distances that we found in the two subproblems. And let me just assume that delta P is less than delta Q, so, and I'll just call that delta. So remember the recursive structure. You have to convince yourself that we really know this at the time when we're trying to do step 5. So we've divided. Recursively, we're making these recursive top-down calls. Divide, 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 divide. You finally get down to something, a base case, which I haven't written up, but it's clear enough. If you get down to a side that only has 2 points, you definitely know what the shortest distance is. And then you're coming back. The recursion is finishing some level and starting to come back. And so when you come back and you get to here, you have in your hands an actual delta that was the smallest that you've seen so far. So you can use that at this step. Okay, there is a delta that you're aware of. All right, so let's just start looking at some geometry and what we can say about the candidate pairs with respect to delta. So here we are. Here's P. Here's Q. And in very quickly looking at the book before the lecture, I couldn't figure out whether they intended Q to be on this side and P to be on that side. But so again, when you look at the actual writing, the way they've written it, it may not exactly correspond to the way we're doing it here, but certainly the ideas are the same. Okay, so this was the median dividing line, and there's no loss in assuming that one of the points here is actually on that line. Half are to this side and half are to that side. Let's just say that there is a point in P that's actually on that line. Okay? So this line is called L, and the point has x-coordinate x star. It has some y-coordinate also, but we don't need to pay attention to that right now. All right, so the first observation that they make is that here's P. Let's assume this is distance delta, and this is distance delta. Okay? So x star is obviously the rightmost point in P, because it's on that dividing line. There's really nobody else beyond there in P. And this is a distance delta that we've gone back to. And this is distance delta. Okay, so here the first claim is if there's a point, xy is a point where x is less than L minus this delta, then xy can't possibly be in the closest pair crossing L. So remember, we already know what the closest pair is strictly in P, and we know what the closest pair is strictly in Q. So we're only looking for those pairs that are the closest among that cross L. So one is going to be in P and one is going to be in Q. And if we have a point here, I don't mean to make it the same L as same Y as that, but let's take a point here, which is to the left of L minus delta. Okay, so there's no way that this can be among the. Oops, I didn't mean to say that. Can't be in the closest pair crossing L. It might be actually. Can't be in a pair crossing L that has a distance smaller than delta. That's the way I wanted to put it. Okay? So this point is to the left of capital L by more than delta. And therefore, what's the shortest distance from this point to any point in Q? It's got to at least be delta. There's no way for this point to get to L and beyond with a distance less than delta. Okay? It could go off at a different angle, but that only makes things worse. Makes it longer. So the distance from x, from this point over to anything in Q is at least delta, and therefore that pair will not be the overall winner. Okay? We're looking for the overall pair that's shortest among all the pairs of points. And so you don't have to think about such a point. Okay? That's useless. Well, same thing over here. Any point where the x-coordinate is bigger than L plus delta, so x is bigger than L plus delta, that's a loser also. Okay. All right, so we know when people said, and somebody said earlier, you just look close to the border, this quantifies what close to the border means, at least in terms of the delta that came from the subproblems. Okay, but again, that by itself is not enough, because you might have n squared of these pairs. You might have all the points in P here and all the points in Q there. So until we look at that possibility, we don't know that that's the case. All right. And at a point of implementation, how would we find all of the points that are within delta of L? Okay. Well, remember, we're trying to do this merging, or coming back from the recursion, in a time bound that I just erased. This is our goal, T of n, remember 2t n over 2 plus some constant of n. So we're in step 5 over there, and we're trying to implement that in something that's proportional to n. And we've just realized that we don't have to look farther than delta to the left, and we don't have to look farther than delta to the right. How do we find the points that are in there within this time bound? Well, we just look through all the points in P. If we have P in some list, there's time to look at them all, and we just check what their x-coordinate is. We know what L is, and we just figure out which ones are close enough. And there's plenty of time to do that, because this is our time bound and there's only n points. And similarly on the right, we can do that. So restricting the points to the ones that are in this interval that's not an issue and not difficult. Okay, so now you have, let's say, a point here, xy, that's in this interval. And so we can't exclude it yet as being in a pair that actually has a distance smaller than, put in a slight angle here. Maybe this distance is less than delta. So we can't exclude this one yet. And the obvious thing we could do, of course, is just take a look at x, y, and every other point that's in this slice. Right? But again, there may be too many of them. We still haven't restricted how many there are over here. Okay? So and we won't restrict the total number that is over here, but we will restrict how many of the points over there we actually have to consider together with this point. And we'll also have to look at the implementation of how we find those quickly. All right, so the book says that for any point here, there's at most 15 points on the other side that you have to look at. Okay, now the 15 is a little mysterious. I think it's easy to see 30. You can be even more clever and get down to 8, I think, or something. Anyway, it doesn't matter. It's a fixed finite number that's independent of n. And so that's what I want to show you at this point. And then we'll have the implementation question of how do you find those quickly. But what you can see, though, is that for every candidate on here in this slice, if it only has to look at some fixed finite number of points over here, whether it's 30, whether it's 15, whether it's 8, whether it's whatever it is, it's a fixed finite number independent of n, then for it looks at those fixed finite number, figures out those distances, and for every other one that's in here, it does that for its list of 15 or 30. And therefore, the total amount of work that would be done in this phase 5 would be proportional to n. There's n points over here, and they're only looking at, let's say, 15 other points in Q. Then we definitely can achieve this bound. And the solution of this recurrence is n log n, and we've done what we claimed we would do. OK, so where does this 15 come from? So I'm going to basically draw this again, but without all the clutter. So here's, this is the dividing line L. And now I'm going to take another line here, which is delta over 2. Okay, and another line, which is delta over 2. Okay, And then I'm going to divide up horizontally in increments of delta over 2 also. Okay. So let's just look at, let's look at some sort of in the middle, a little bit easier to look at. Delta over 2, delta over 2. So we divided up this slice over here a little more finely, both in terms of the x-coordinate and the y-coordinate. Okay. So now you can ask, how many points? Oh, actually, I think they give a name to this set of points over here. So S equals the subset of P in the delta slice. Okay, so S is the set of points. And P, of course, itself was a subset of capital N. Capital N was the whole set of points. All right. Now, here's the question. One question. How many points in S can be in one of these boxes? Delta over 2 by delta over 2 boxes. Any answer? Yeah. Just one? Is that what you said? And why is that? Yeah, if you have 2 in here, well, let's just make them as far apart as possible. Let's say they're in the corner. Okay. So what's the distance between them? This is delta over 2. This is delta over 2. So that distance, 2 points in a box have distance less than or equal to delta over 2. So delta over 2 squared plus delta over 2 squared square root, okay? Which is equal to delta over 2, right? That's a square root of 2. Anyway, it doesn't matter. Less than delta. Okay? But we said that delta was the smallest distance among any pair of points in P or Q, in fact. So you can't have 2. I picked the 2 that are farthest away. Obviously, any 2 that are not on the corners are even closer. So if we had 2 points inside this box, or even at the corners of the box, we would contradict that delta was the smallest distance that's found so far among the points in P or the points in Q. All right. So now let's consider a candidate. There's some point which is in this delta slice, and arrange the boxes so it's on the same x-coordinate as that point. All right. So I don't think anyway, here's a point, xy. Okay? We wanted to argue that, I should make one other point. The same kind of conclusion holds on the right side. Okay? So if we look at these boxes over here, this is delta over 2, delta over 2. And we similarly know, delta over 2, we similarly know that we can't have, I think I want one more. Oh, we want to go down this way too. Getting kind of cluttered here, but I hope everybody is seeing what we're doing. Okay. So here's a point, a candidate point in this delta slice. And we have to consider some points over in the other delta slice in Q that might be together with this point to have a distance less than delta. It might be a winner in comparison to the best we found so far. All right? We just argued that over here, you can have at most 1 point per these boxes, right? And I've drawn these out so that there's 1, 2, 3, 4, 5, 6, 7, 8. I mentioned an 8 earlier, right? A 15 and an 8. Let's see if this works. So there's at most 1 point in these boxes. If you look beyond those boxes, well, we know if we look beyond that way, the distance is too big. It's bigger than delta. I mean, the other point together with this one has to be within this delta slice. So there's no point in looking that way. If we've gone up here 2 of these boxes, so this distance is delta, right? So I put these boxes so that they're aligned with this point xy. All right. Is there any need to go up in this direction? A point that's above. I've written 4 boxes here. Is there any reason to look above 2 boxes that are above this one? Well, this is delta over 2, delta over 2, so this is delta. I guess by diagonal, yeah, okay, so by diagonal you could certainly possibly get to some point over here that's distance less than delta. All right? Well, but if I go up, so this is the 8, and if I do another 2 levels, okay, now this distance is 2 delta. Okay? That distance is 2 delta, and if you go by a diagonal, and I think that's enough. Anyway, there's some finite number of these boxes where even along a diagonal, well, yeah, the diagonal is going to be bigger than that coordinate anyway. So certainly, going up 4 boxes is of no use, right? And going down 4 boxes is of no use. And if there's at most 1 node, 1 point per box, now we're talking about 16. Where did the 15 come from? I don't know. By looking at this a little more closely. But if you look at it more closely, you can get down, I think, to 8. But it doesn't matter in terms of our business here. We're trying to get this CN. So certainly, now 16 boxes is enough to argue that any point outside of these boxes there's no point outside of these boxes in Q that could be the paired point with xy to have a distance less than delta. It's just by simple geometry not possible. Okay? And as I said, you could be a little more precise and look more closely and go from 16 down to 15, which is what they do in the book. But I think if you can get to 15, you can also get down lower. So, enjoy yourself if that's what you want. But anyway, for our purposes, we have shown a finite number like 16, which is sufficient. Does everybody get the idea? I think I'm really belaboring this just because the geometry. Yeah.
So is the number of boxes proportional to the range of the y values?
No, the number of boxes came from delta, and delta was the value that gets inherited as you're going up the recursion or you're coming back from the recursion. But the point is that what we're seeing is for each candidate point in this delta slice, there's at most 16 points on the other side that could possibly be paired with it to have a distance less than delta and therefore be a winner. But your question was what delta depends on?
Well, I was thinking your XY example they have there, in order to know how far up and how far down on the Y scale, so I was kind of curious on how many deltas there.
Oh, okay, maybe you're anticipating the next point. All right, the next issue, yeah. Okay, so what we've proven is that for every point, there's at most 16 other candidate points in Q. For every point in P, there's at most 16 in Q that could possibly be paired with the point in order to have a distance less than delta. Now, how do we get our hands on those? Okay. Yeah, all right, so I was a little premature in saying that we can achieve this time-bound without worrying about that issue. Okay, so how does the algorithm get its hands on it, knowing the fact that's there? All right, so here's the question. Let me just rewrite. Currently, we know that for every point xy in P, there are at most, I'll use 16 points in Q that might be paired with xy to get a distance less than delta. And any other pairs are irrelevant because they have distance bigger than delta, or bigger, yeah.
Is the maximum number like 5?
You're saying the maximum number is actually 5? Well, as I said, you could look more closely at these things and get a number smaller than 16. That's for sure. I don't know off the top of my head whether that number is 5 or not. It's a good thing to think about, but yeah. So I vaguely remember that certainly 8 is I remember that 8 was a bound that you could put. All right. But this is a finite number, independent of n. Okay, but the issue is, but how do we find, we being the algorithm, find those 16 for each, now you have to do it for each one of the points in the slice, for each, actually this is more precisely in capital S, for each point xy that's in capital S and within this time bound. Well, at the very beginning I said it would be useful to have the points sorted by y coordinate as well as by x coordinate. And in fact, when we do this splitting into P and Q, what we're going to do is also the time it took to split, that could be proportional to n. And we therefore have enough time to look through all of the points. Once we've identified what's in P, for example, we have time to look through the sorted Y list and pull out in order the ones that are in P. And similarly pull out, well, at the same time, pull out in order the ones that are in Q. So you have, at every level of the recursion, you have the elements in P and the elements in Q in X sorted order and also in Y sorted order. So we'll want that at every level of the recursion. Now we're looking at coming back from the recursive calls, and so we have the list of points in Q that are sorted by Y coordinate. Okay? So how do we get, let's say now we're going to look at each of the candidate points in this P slice, and we want to find the points over in Q that are among its 16 candidates. Well, we also have the points in the slice we have the points in P sorted by Y coordinate, right? That's what I just was saying. So let's in order to implement this step, let's just look through them in order. When we look at a point, we can also determine is that in this slice or not. Okay? So let's say we found a point that's in the slice. That's over in this picture, xy. It's in this slice. Okay? And we've been working our way up in the sorted list. The y-coordinates were here. Okay? And we've been finding for each point that's in here its candidates over in Q. Remember, those points are also, we have a sorted list by their y-coordinates. So we're working our way up in that list too. Okay? So when we get to this point, the candidates we also have to have filtered for sure Q to be in its slice, all right, which we have time enough to do. So imagine we have the sorted list of guys in Q that we've looked through to find which are in this in here. Okay? So we have this guy's y-coordinate, and we have the y-sorted list of the elements in Q that are over here. All right? With respect to this one's y-coordinate, this tells us that in terms of the y-sorted list over here, we only have to go down 16 places and go up 16 places at most. Okay? Again, if we filtered so that we only have in our hands, and we have them in sorted order, we only have in our hands those points over in Q that are in this delta slice. And we know that in terms of the that there can only be 16, actually there can only be 8 going down and 8 going up, points that are potential, that are in these boxes. Okay, that's what we argued earlier. So if we know the y-coordinate of this point, and we can look inside this list over here at that position, if we go below that by actually just 8 positions, we'll have captured all the ones that are in here. And if we go up by 8, we'll have captured all the ones that are in there. And even more, perhaps. And then if we do the distance calculation between this point and every other of those 16 points, then we will have definitely considered all the pairs that were necessary. Yeah?
So you're writing down the P list at the same time as you're writing down the Q list, as if you were going to merge them. So you're at the same, so the point you're at in P is near the same value that the point you're at in Q. So you can just go up Q and back down Q.
Yeah, so I think the comment is that the way I described this was a little clumsy, and that one could even be a little more efficient and implement it more efficiently. But the way I did it, it still works to, I mean, you're working your way up, and so for the next one, you know you only have to look that many positions down or that many positions up. Or if there are more than those that haven't been removed here, you can remove them up until there's just 8 left here. And then you have to look forward at most 8 as well. Okay? So those are implementation details that are necessary in order to get this result, but quite simple ones. All right, did everybody get the big picture of how this works? So there's that implementation detail at the end of keeping the Y lists sorted, and as you do the recursive subdividing, to keep those as well. So again, now we've really considered all the details of the algorithm, and we're within the Cn, and the recurrence relation solves to n log n. Okay, so I'll be back here at 6. If anybody wishes to join me, that's fine. Thank you.